Greetings, building science enthusiasts, and welcome back to our podcast. This episode is brought to you by our dear friends and colleagues over at Reisinger Homes. They're an Austin-based, full-service luxury home builder and remodeler, and we've worked with them on many occasions. And Reisinger Homes really is a different kind of firm. First, they're focused on building science, which we think is incredibly important, and I encourage you to check out the YouTube channel of their owner, Matt Reisinger. It's at youtube.com/user/Matt Reisinger. Be sure to subscribe. And secondly, we've seen time and time again how much architects really appreciate the seamless experience of working with a builder who has an in-house architect/builder. Reisinger Homes has exactly that person. His name's Eric Rouser. So architects, call Reisinger Homes early in the design phase of your projects so we can team up with you and your client to build a great home.
Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas.
Okay, hello, and welcome everybody. Welcome back to the Building Science Podcast. I'm Kristof with Positive Energy here in Austin, and I have two guests today. We are talking about indoor sound quality. This is part of our indoor environmental quality series, and I'm very pleased to have with me John Poesnecker and Keith Simon. John is a PE and a mechanical engineer background from Auburn University. He worked for many years with an acoustical construction company, working with acousticians and acoustical consultants. He is currently the Grand Poobah and a senior engineer at Terracon and a BES principal. Keith Simon is a senior architect at BES Terracon. He's also an adjunct faculty at the UT School of Architecture. He is also a friend of the podcast and a frequent contributor here. You've heard him before. Welcome, gentlemen.
Thank you.
Good to be here.
Yeah. So the topic today is sound. We're going to focus it mainly for general indoor acoustics for residences and commercial. There are lots of specialty environments that we need to have special considerations for. Some of that might come up during the podcast. Some of it might not. As a mechanical engineer doing design of heating, ventilation, air conditioning systems, sound is in my daily repertoire. It's something I'm thinking about. We always want to move air fast enough to get it to throw and mix in the room to make the space comfortable, but slow enough so that it doesn't make sound. And actually, John just pointed out, we were talking before this, that sometimes you want that, right, John?
You can put white noise generators, or you can have the air velocity do it for you.
Yeah. We've talked about that actually on a different podcast. I don't know if it came up, but I know we've talked about radiant heating and cooling, and I heard about I believe it was an office space in Washington D.C. where they went with radiant heating and cooling, and it was so quiet that it made people, like, every time they would talk, you'd hear it across the room. And
in an open office concept, you want some privacy, or at least from the speech intelligibility, so that they can't understand the conversations next door.
Yeah, that's exactly right. Yeah. So there's speech intelligibility where you want some noise. There's also your bedroom where people typically want it pretty quiet, right? Or is white noise appropriate in a bedroom? What do you guys think?
Probably not. So usually, well, let me just jump into here. One of the common misconceptions with acoustic design is using taking a room and designing it acoustically for the wrong properties. So in other words, some spaces reverberation is a good thing, like a performance space think of like the extreme, a Gothic cathedral, where the greater the reverberation, the better. And we can actually define it and say it could have like an 8-second reverberation time, meaning that when a sound is created, it takes approximately 8 seconds for that sound to degrade 60 decibels, essentially vanish. But then it depends on the kind of space. So let's say we're talking about a space that's designed to promote talking, like a classroom or a lecture hall or a podcast studio. Then your goal reverb time might be about 1 second or less, maybe like 0.8 seconds. And then, so you don't want too much, because if you have too much reverb, then the sounds mix together and there's unintelligibility. John's already ready to disagree with me.
Well, the type of music that you're putting in that space, or
as you'll learn, Keith and I debate all the time about this. So a live room isn't necessarily bad if it's the reflections are
live
controlled.
room meaning what?
A more reverberant room.
Okay.
So
Hard
a
surface.
large auditorium. You don't want to deaden it completely. You want it live so you don't have to have as much amplification of the sound and have natural sound. But you've got to control the reflections. So if the reflection, you get 4 or 5 different reflections hitting the audience from different locations at different times, you don't understand what's being said. But if you control the reflections so that you don't get those delays, then you hear it without much amplification.
Right.
So I actually do agree with John on that. Maybe I just didn't explain it well. You never really want 0 reverb time or the least amount of reflection at all. Like even in, say, a classroom setting or a lecture hall, if you had close to zero reverb time would be outside, right? Outside there is no reflection, so any sound never comes back. It's all one directional.
Unless you're in a canyon.
Right. And then you get into echo, which is related to reverb, but a little different. But anyway, if you had close to 0 in a space, number one, the person speaking wouldn't be able to hear themselves, and they would start talking louder and louder and louder to make up for it. So that's not really what you want. But certainly, John, you can agree with me when I say a long reverb time, something extreme like a Gothic cathedral, would not work for a lecture, because that sort of mixing of sound that works for music is detrimental to listening to the human voice.
I'll give you a point there. But you can control the reflection and diffuse that reflection so that it's not one directional.
Right. And so, but we should probably talk about massive, hard, reflective surfaces versus soft, squishy, absorptive materials.
Correct.
And so when you're designing a room acoustics, first you have to decide the goal, like, do you want to promote reflection or do you want to limit reflection? So earlier we were talking about an open office plan. That's the kind of space you really want a lot of absorption and not a lot of reflection, because people talking can annoy people who are nearby, or even worse, it could be a privacy concern. And so that's why there's a drive in office areas to the extreme to have lots of gray squishy materials so that you have a lot of sound absorption. And also, for other reasons too, the lighting, it gives homogeneous lighting.
Okay.
And these...
I was wondering how gray affected the sound.
yeah, exactly. That's more about the homogeneous lighting, homogeneous sound, and ultimately it frequently open offices are pushed too far in that direction, I would say, and it can be a little bit soul-sucking. So there has to be a little bit of a balance.
Is that a technical term?
Yeah,
soul-sucking is measured in
absolutely
dB.
And you see more of the fabrics and absorption materials, right? Not the hard finishes and floor surfaces and ceilings that are hard.
That's right. Carpeting, for example. You could have an acoustic ceiling tile or acoustic ceiling panel. There are lots of ways to introduce soft materials as opposed to just the squishy gray cubicles in an office area. But there's another misconception which I want to point out, which is there's room design and room acoustics, and you have to have the right goal. Do I want to promote reverberation or do I want to limit reverberation? But there's also noise control between 2 distinct spaces. So that's the partition that's separating those 2 spaces. The strategy for that is massive materials. You don't want to rely on soft, squishy materials, because then sound can transmit right through those and won't be and so a mistake, for example, that's frequently made in an open office environment is that the partition doesn't go all the way up to the roof deck. It stops at the drop ceiling level, and what happens is the sound from one space transmits, some percentage of it transmits through that ceiling tile and bounces down in the space next door. So you do need to provide the partition all the way up to the deck. And sound, being a fluid medium, can easily be short-circuited. So if there are breaches in that partition, say an electrical outlet that's not well sealed, it doesn't run to the deck, a keyhole in a door, you can actually get a lot of sound transmitting through those little breaches.
And a couple of concepts. So to block sound, you typically add mass, right? And that your good barrier materials are very dense materials. Also, if you get variations in layers of different densities, it tends to block the sound. Over the top of a partition wall, above an acoustical ceiling is a typical area. A lot of times we'd hang loaded barium vinyl, very dense vinyl that's about an 1/8 inch thick. To create a barrier was less expensive than framing the wall up to the deck.
Interesting. And that was to create acoustic privacy between two adjacent offices.
Correct. Then the other means is the ductwork. Right?
Yes.
That transmits noise. So you may have a common duct that runs between offices or rooms, and it's a great conduit for noise. And typically the interior of the duct is very reflective and carries it down.
Right.
And then the outlets, it's surprising how outlets or door thresholds and seals, very small cracks, almost like when we talk about the envelope and air barriers.
Yeah.
You can think the same way with your acoustical walls and ceiling for noise. Very little cracks, noise transmits. It's amazing how it transmits.
And they make acoustic caulks and acoustic putties and things like that.
To seal up, right? Seals and gaskets.
Yeah, it's interesting. John and I do a lot of consulting on multifamily construction, and multifamily construction sometimes can be notorious for not being sort of penny pinching in terms of the building enclosure. However, we walk around these multifamily and they're actually really sort of impressive in terms of their acoustic control between units. You see a lot of double stud walls so that there's not continuity from one side of the partition to another.
Just to raise that STC rating across that wall.
Yeah, STC, so that stands for Sound Transmission Class. And that's a rating of how much noise is transferring through a partition. So, for example, if it's an STC of 55, then that means the sound that on one side of a partition reduces 55 decibels to the other side. So the higher the STC rating, the more sound is being blocked from transmitting. And then we see other strategies such as resilient channels, which is like these little... How would you describe that? Like a metal channel.
Like a hat channel?
Yeah, like a hat channel, but with only a flange on one side. So you can imagine it's attached to the studs, and then the drywall is attached to the resilient channel. But if the drywall vibrates, it's less. It has less ability to immediately transfer that vibration through the partition. So there's a lot of actually pretty interesting strategy.
And that kind of leads into the concept of structure-borne noise. You put the resilient channel so you minimize the sound vibration carried through the structure to come out the other side. There are cap ceilings, gyp ceilings that are hung in isolated hangers that prevent the vibration from going through the deck above and increasing that STC rating.
I see.
So let me define vibration for a second here.
Right, so vibration is separate from sound.
Well, okay, so let me back up a second.
Talking about structure.
If we're going to define sound, we usually
Let's define sound.
Yeah, all right. So we can define sound in terms of frequency and amplitude. So if we think of sound as a wave phenomena, and you can imagine it as like, we can represent it as a sine wave. And the height of that sine wave we call the amplitude. The higher that sound wave is, the louder. So amplitude is volume. And then there's frequency. So that sine wave, if it's going up and down within a certain amount of period lots of times, that's high frequency. It's a higher pitch. If it's a much longer sine wave, it's lower pitch. And at our threshold, our ears can only have a certain threshold that we can hear. If you go so low, such a long sine wave, that we can no longer hear it, but we can feel it, that's vibration. So vibration is basically sound energy that you can't hear, but you can feel it. Now, in terms of building acoustics...
When it's in the air.
That's right.
No, not when it's in the air. Well,
so vibration
everything you just said is relative to the medium that's carrying the wave is air in our ears.
Correct.
When you go from air into another substance, water, the building structure, concrete, wood, it's a little different, but same concept.
Right. All I was trying to get at there was that usually when we're talking about building acoustics, the medium through which the sound energy passing is air. That's most of the time what we're talking about. But structure, steel, wood, concrete, becomes extremely important when we're talking about vibration. And it becomes so important that if we're talking about a high-rise and the mechanical room is in the basement, and there's no sound decoupling of the mechanical system, that hammer strike can be felt in the penthouse, 100 stories up.
But think of it as still a vibration through the medium of the structure rather than through the air.
Mm-hmm.
Right? So it's still a wave pattern that goes through the structure.
Right.
And I always was amazed, if you think of whales in the ocean, their sound travels a huge distance, much faster than the distance it would travel in the air, in the speed. Mm-hmm. And the medium makes that difference. It's really and in a concrete structure, it's really odd how an impact 10 stories down, for some reason, will come out above with about the same sound power or loudness.
Yeah, and it has to do with the density of the material. So the denser the material, the faster the propagation of sound energy. So for you musicians out there, you can imagine a tuning fork, and you strike it, right, and you hold it in the air, and it's a certain volume. And then if you take that tuning fork and you put it on a table, for example, all of a sudden it becomes much louder, right? And that's because the sound energy now is transferring through that dense material of the wooden table.
Interesting. That sort of surprises me. So I
got to think about that one.
If I take a tuning fork and I touch to the table, I feel like it's just going. It's just going to damp out and stop making sound.
So Miguel's a musician.
Am I holding it near the table but not touching it to the table?
No. If it's transferring through air, the second you touch it to the table, it becomes very loud. I wish I had a tuning fork so we could play it right now. But you know what I'm talking about, right?
So when you take a tuning fork and you strike it and it's vibrating, when you touch it to a surface like this, it will simulate an amplifier, basically. But the sound is going to pitter out faster than it would had you just kept holding it up in the air.
So basically, in a tuning fork, it's all coming out in the air. Once you hit a solid surface, it now reflects back up and increases the sound power. So it's kind of like another concept in a gymnasium. If you have a very reverberant room and you have a sound source, the reverberations bounce back at you. So you're getting impacted by the same source several times. So you get a higher level of energy and sound. Where if you stop the reflections with absorptive materials, the sound level goes down from the same source.
Right, and then another good way to think about it is the difference in loudness between a string pluck on an electric guitar and an acoustic guitar.
Yeah, that's a really good comparison there, and sometimes that's the case with performance halls. In other words, if a performance hall is designed well for a certain kind of performance, whether that's opera or music or plays where it's speech, you probably don't need electric amplification because they're wherever you're sitting within there, the reflections are going to be the same experience throughout. However, if either it wasn't designed well, or you want to do a kind of performance that it wasn't designed for. So, for example, it's designed for, say, a chamber quartet, and then you want to have or the opposite. Let's say it was designed for an opera, and then but you want to have a chamber recital in there. Then you may need electronic reinforcement or an electronic sound system, basically to make up for the lack of natural acoustics that are occurring in the space. And so this goes back to our early discussion about white noise, which is, we've sort of jumped right into, like, you can use white noise to drown out sounds or noise, unwanted sounds, discussion, etc. But I would argue that that's sort of if it wasn't designed right. If it was designed correctly, you wouldn't need the white noise. And so I've never actually seen a mechanical system that was intentionally designed for white noise. I've seen it being, it happens to be good white noise, but I'm curious if you guys have actually intentionally done it that way.
I have not.
I've seen where they've modified the mechanical system so they reduce that noise.
Oh, yeah, absolutely.
And then we came in and added, or a contractor came in and added white noise generators.
Correct. Right. So, like, co-working spaces, you actually want some white noise.
Because the hissing sound usually out of a diffuser is at that speech frequency. Mm-hmm. It creates that. And that's what it is. It's just creating a noise that's at the speech frequency So that, and it's not saying you're not going to hear the people talking next door, but you won't be able to understand the conversation. That's the speech intelligibility part.
So I'm going to say something that I know is going to make John's eyes roll. And our listeners won't be able to have the fortune of watching him roll his eyes now. But I would say white noise is when you throw out a bunch of frequencies to just generally obscure the sound so there's no intelligibility. Pink noise is what you just described, which is it's frequencies that are specifically selected in order to drown out the human voice. So that's what my understanding is what pink noise is. There's also acousticians out there who are developing other noises. You can go to Wikipedia and read about brown noise and blue noise and red, and that goes way beyond the scope of building acoustics or what I understand. But from my understanding anyway, pink noise is specific frequencies to drown out human voice, and white noise is kind of just throwing out a whole bunch of different frequencies and drown out everything.
And surprisingly, I agree with you. I've heard the concepts. I don't know if it's pink, blue, or green, but there are different types of noise generators for different reasons. Mm-hmm. It kind of makes you talk back into now active noise control is another feature that if you have a constant noise source, they design another source that reflects the sound waves so that you don't hear that noise.
Exactly. And you can electronically create.
In power plants, it was really effective because you had that constant turbine frequency that you could very well, in headphones, negate by another source bouncing that sound back. It's an interesting concept.
Yeah, and they're using something similar. I mean, you can do electronic sound design in lieu of architectural sound design. You can fix a space or damage a space. I guess you wouldn't want to damage electronically, but what they're doing is they're taking like a small room and you can make it seem like a concert hall, or you can take a concert hall and make it seem like a small room with these sensors that pick up sound, and then an adjacent or some other speakers electronically coupled to make the offsetting frequencies.
Right. And a lot of times in big stadiums, they're there for sporting events. They're not made for concerts, but they bring performers in and have concerts. So it's a fairly sophisticated amplification system to get good quality of the performer compared to what the facility really does. It's not an acoustical type facility.
Right, good.
We simulate something very similar in this very podcast with the very few microphones that we have. I take the audio that's recorded with these microphones and actually run it through multi-band equalizers that are meant to weaken or strengthen different frequency bands. And so there are different parts of the frequency that we hear that make something sound very robust on a recording or very natural. But if I, jammed things up right in the middle of the frequency bands that you're used to hearing, it's going to sound like you're talking in a tin can.
Wow, maybe you can do that.
All right, so yeah, let's do that. So let's simulate what reverberation actually sounds like. Reverb. So what you've just heard is essentially a digital simulation of what Keith was discussing earlier. That reverb, the reverberation, it's basically just the persistence of sound after the sound is actually produced. And that persistence is caused by reflections of that sound on different surfaces. So it could be just a single reflection and you hear a slight, very tiny reverb, or it could be a number of reflections and you hear that deep well-like sound. But eventually those surfaces start to break up the sound waves, and that's what we call decay, and that's when you actually hear the sound start to cease or taper off. In a similar boat, it's easy to imagine a sound actually echoing, like in a canyon. Here's what that sounds like. Echo! Echo! So what you're hearing there is actually the reflection of a sound that arrives to the listener. And of course, again, this is digitally simulated, but after the direct sound is produced. So that delay is proportional to the distance of the reflecting surface from the source and the listener. Obviously, you don't want to have a lot of echoes in an indoor environment. And here's what it sounds like whenever we crank the mid-range really high. And now the upper range of our frequency bands. And now the lowest of our frequency bands. Long story short, sound is complicated, and there are a lot of fun ways that you can manipulate it digitally. But back to the point of the podcast, it's important to get this stuff right, because you can't digitally simulate your actual experience inside a piece of architecture. So
I think the subject, though, of different performance venues and the types of music that fit in them is really fascinating. And there's actually a 15-minute TED Talk you can find on YouTube by David Byrne of the Talking Heads, where he kind of gives a history of different types of venues and the types of music that fit in them. So stadiums is like, there is zero reverberation. It's outdoors. It's all one directional. But another one that's sort of fun to think about is reverberation. Reverberation time is based on two factors. One is the amount of reflective and hard surfaces in the space, but also the volume of the space. And so a Gothic cathedral with an 8-second reverberation time can some way be mimicked in a racquetball court, because even though the racquetball court is small in volume and it's got all these hard surfaces. So that's another fun thing you can see on YouTube, that there's like this niche of musicians who perform in racquetball courts because it's kind of like an easy access way of performing at this very special musical environment, instead of having to travel somewhere to find a Gothic cathedral to perform in.
Interesting. So that is very interesting. And I want to go back. You were talking about sort of architectural acoustic design of these multifamily buildings. So besides making sure adjacent spaces, like different apartments, so interspace acoustics is not happening, do you think they're doing other things, like shaping rooms in certain ways or choosing materials for rooms to promote good acoustics? Or?
No, nothing that sophisticated. So code will require multifamily to have a certain STC rating between partitions, between spaces.
That's right.
And really, that's, like we said, an STC rating. There's also IIC, I believe that's the right term, impact and isolation class, which is floor to ceiling. Mm-hmm.
They also have the STC requirement on the floors and an impact rating on the floors.
What does that mean, the impact rating?
It means if you walk on a floor, like I'm tapping my finger on the table, you hear it on the floor below.
Correct.
That's the impact noise traveling through the structure. So they'll do a couple of things. One, they'll increase the STC rating by pouring gypcrete on the floor and providing a mass layer, right? And then they'll have a sound deadening pad below the gypcrete to reduce that impact noise, because you're adding a hard surface that will pick up the noise, the impact noise, but then they put a layer so it doesn't transmit to the floor below.
And you get additional mass, and you get changes in mass in that assembly.
Right.
So all that, just a way to point out that this concept of interior sound quality, I talk a lot about interior air quality, which you take pretty specific measures. What do you bring into the house? How do you filter it? All these things. But sound quality considerations are somewhat implicit in conventional construction paradigms, right? I mean, it's just sort of built in, like this pouring gypcrete and putting this pad. People might not know why they're doing it, but they always do it. I guess they know.
There are things in just your house, right? That a garage door opener, it transmits noise into your structure, and you hear it throughout the house sometimes.
Yeah. And
a lot of times people would put a home theater above their garage and would go crazy with the garage door opener. So you have to isolate that noise source from the structure.
Yeah. With a vibration isolator?
A lot of times they would do that.
Yeah.
Either you put a floating floor in to isolate the floor from the structure and your walls, or you hang that garage door opener and isolate it from the structure. The other thing that's interesting is the shape, say, of especially ceilings, maybe in commercial buildings.
Interesting.
Barrel ceilings are really neat, but they have a focal point for the noise. Domed ceilings in some rooms or churches are popular, but they have a very distinct focal point. And if you ever go to Las Vegas, and I think it's the Forum, has several large domed areas.
Yeah.
Have fun and just walk through the center of the room, and you'll hear that noise all of a sudden just triple in sound in the center from the focal point. So just the shapes of your rooms, make a big difference.
Yeah, I want to add to that that there's concave and there's convex. And so concave, like John's describing, of a dome, for example, has a tendency for sound to creep along it, and also focusing, that instead of spreading out the sound is focused to a point. So concave shapes have a tendency to be very bad for room acoustics. The opposite, convex shapes, are actually really good because the sound energy bounces off convex shape and is spread throughout the space. So as an example, if folks are familiar with the main lecture hall in Goldsmith at UT, the architecture building, along the side of the walls there are all these stones in convex shape, or sometimes like the inside of a guitar or a violin, it's convex, and that allows the sound to be spread out. So that's one thing. And then the other thing I wanted to mention was there's some interest in prefabricated construction. And so one of the inefficiencies of, imagine like a multifamily area where you are going to, in a factory somewhere, fabricate each of the living units and then ship them onto site and put them together as Lincoln logs. Well, the inefficiency with that is it has to have all of its walls and roof and everything. So when it shows up, there's two walls. So in terms of cost and efficiency, there's an inefficiency to it. But for a construction project like multifamily or apartments where acoustic separation between those units is really important, it's awesome because they're completely isolated from each other. So that's an opportunity where prefabrication might make sense.
Mm-hmm. So I've been in a lot of restaurants recently, switching to sort of the human experience in a commercial setting, and found that I'm sitting across the table from my wife, and I basically have to shout at her to be heard. And my wife's kind of soft-spoken, so I basically can't hear her. And yet, these are very popular restaurants, and no one seems to notice. And I happen to have a sound meter on my phone, and it's measuring sound power. No, it's measuring sound pressure. And by the way, all you guys listening, you can download, just go to the App Store and put in sound meter. You can pull one out. And it's like at 85 dB, right, in this restaurant. And so I'm curious, I know I put a number to it, but do you guys have is there a target number when an acoustician is designing the sound pressure for a space for humans to talk? I mean, I guess there's a certain frequency range as well.
A very non-scientific theory there is, it depends on the restaurant. If they want to have tables turned several times through a night, they don't care about the noise level.
Oh, interesting.
If they're a high-end restaurant that's willing to have one table sitting per table per night, and they want that to be an experience.
Oh my goodness, John! So you mean
So,
they're basically?
I don't know if that's
I say,
true,
let's get
but
out
I've
of here,
always
and the
heard that
restaurant's
about
like,
restaurants.
that's great.
Right.
So when I say to my wife, "Let's get out of here," I can't hear what you're saying. The restaurant's like, "Good, next client's gonna be sitting."
So I've heard that theory too, that they actually don't want you to be too comfortable because they want high turnover on the tables. The other theory I've heard is that by being loud, it feels happening, like it's a hot location.
Yeah.
It's a lot of energy.
Personally, I don't believe either one of them, because especially for a high-end restaurant, and I don't want to mention any names, but this is a wonderful restaurant, really expensive. Why would you want to chase people out and make it feel happy? You don't have to do that. You want people to be comfortable. Yeah. So and at that particular restaurant, I went up to the maitre d' and said, "Are you happy with the acoustics in this place?" She said to me, "No, they're awful." I said, "Well, adding absorptive material to make it a more comfortable environment is not that hard to do." So she wasn't particularly interested in hearing my the services I had to offer. But I find that's true a lot in restaurants around town. I have a more cynical view of why that is, which I believe that our generation of architecture is, to quote Juhani Palazma, is focused on ocular centrism, which means the above and beyond, it's all about what it looks like,
yep,
instead of the experience of it. And if you care about the experience of the design, then what it feels like in terms of temperature, what it smells like in terms of indoor air quality, and what it sounds like can not only be as important as what it looks like, but a whole lot more important in terms of performance and experience. But unfortunately, I feel like it's just sound is way down low on the priority list.
In for restaurants, and there's a little truth in this, they have some need for cleaning in food service criteria, at least for the kitchen area, that absorptive materials typically aren't favorable to. If you have carpet in a restaurant, it gets extremely dirty fast and requires replacement. Fabric walls absorb a lot of things that a hard surface won't. They're not easy to clean. So there's maybe some truth there.
Mm-hmm.
Interesting. Well, you could do enough probably material on the ceiling and the walls of an acoustic panel that has some ability to be able to be cleaned and handle these,
right,
and have your cake and eat it too.
Right.
Yeah, so that restaurant was at 85. I actually went to a movie theater not too much after that. Movie comes on, and movies are loud when they come on. And it was like, holy moly, this is crazy loud. So I'm holding my ears and I'm like thinking, am I just getting old? I look around, everyone around me has their ears held. So I go out, I took my sound meter actually measured. It was 130 dB, which is like a roaring jet engine, right? So I go out and tell them, and they ended up turning it down. But, it's just striking how...
Theater design is very unique, and you would think it's very sophisticated in its separation between
this was just
theaters.
Up too loud. Uh-huh.
But the sound amplification systems, they take a lot of pride in the different technologies for those.
Do they?
They integrate a little bit in the room acoustics, and they have criteria for each technology what that room acoustic requirement is. But you'll notice sometimes you hear the really low bass noise traveling through from the next door. You never hear the high-end frequencies, and that's the energy levels are different. It's very hard to block a low frequency noise through a wall or a structure.
Mm-hmm. Actually, let's just talk about the frequencies for a minute. So the frequencies, you always hear this from 20 hertz to 20,000 hertz, and hertz is a cycle a second. So Keith was talking about those waves. So 20 hertz would go up and down one wave 20 times every second. But what is it right now? Where I'm talking to you, do you have a sense of what that is?
1,500 is about the average speech range. Is that
that's what I remember, like 1 to 5,000 hertz.
So in terms of the size of these waves, if we're talking about the highest pitch we can hear, like around 20,000 hertz, those sound waves would be like an inch or a couple inches long. If we're talking about the other end, the low frequency sound, think of like...
You're talking about the wavelength now.
The wavelength.
How long it takes.
Yeah, the actual wavelength. If we're talking about the low end of what we can hear, so like a double bass or something real low, but you can still hear it before it's pure vibration, then we're talking like 50 feet long. So, the size of a classroom or a lecture hall, one sine wave, one wavelength would be that long. So, we look at it graphically like a sine wave in order to define wave phenomena, but probably a better analogy to think about sound or the wave phenomenon, sound energy, is if you drop a pebble in water and it radiates in all different directions. So I think that's important, right? It's not typically one direction like a sine wave, but it's all around.
That's a good example. A pebble gives small waves. Mm-hmm. A boulder will give you big waves, so it's like high frequency, low frequency.
Mm-hmm.
Yeah,
it took more energy.
And if I remember, you probably can, Kristof, you've thought about this technically more than I have recently. But the area under your sine wave is the power.
Mm-hmm.
So a long wave with a high peak has much more power than the same peak for a short wave.
That's exactly right.
Which is around, is that 100 hertz level that you're hearing, the low bass through a wall in a theater?
Yeah, and that's why it's so hard to stop, because it has so much power through it.
Right.
To stop that.
So let me try to explain the other reason why low frequency sound, it's hard to stop it through a partition. And going back to this water analogy, you drop a pebble in the water and it ripples out, or imagine in the ocean like actual waves. So the obstruction that wave hits versus the size of it is very important. So imagine like there's a buoy or like a post in the water in the ocean, and you drop a pebble. The size of that post relative to the wave that's coming at it, the post is very large. So when that ripple from the pebble hits that post, it bounces off of it and gets reflected. And that's sort of like high frequency, high pitch sound is shorter and it more easily reflects off of these obstacles. Now if you take that post and imagine a giant wave, like an ocean wave, like a tidal wave, coming at that post, the size of that post relative to the wave is very tiny. And that wave just barrels right over top of it. And so that's the same thing with low frequency sound in music or double bass or vibration. It's very difficult with small architectural elements to stop that sound. And for those of you who can't see John, he's
I'm really thinking hard about that.
he's very skeptical right now.
No, but I agree
to.
what you're saying, because we want to block a lot of sound with very thin elements, and it's difficult.
And sound, I mean, again, it's a fluid medium. And so, for example, the Mopac Improvement Project, one piece of that is trying to block the sound with very large walls on the side of the highway. Well, that is somewhat effective, but one of the reasons why it's not too effective is because the sound that's coming from the highway, it's a fluid medium that can just roll right over that. So it has to be very tall and very close to the source and block the right kind of pitches.
That's true, but on a barrier wall like that on a highway, think of sound just like you do light. It will diffract around a corner, right? Sound does the same thing over the top.
Yeah.
Right? So it's very difficult to build a wall tall enough to block noise 100 or 200 yards away from the wall. Right behind the wall, it does a great job, but not further away, on the street past the wall.
And also,
makes sense.
There's places where you have to get in and out off the highway where obviously that wall is going to stop. So if your house is near those openings, it's going to be much less effective.
Right. The other thing a wall does is reflect the sound. So it may block it from getting right to the other side of the wall, but it reflects it now, so the other side of the highway gets that wash of sound. So the profile on the wall, you'll notice, is sometimes designed as a diffuser. So it's not a flat reflective surface, but diffuses the sound in several directions.
They aren't flat, that's right.
But if you look at highway sound walls in Japan, they're much more, they sort of curve in towards the highway. Almost, if you see them from the outside, it almost looks like the highway's in a tunnel.
To control that reflection from going back.
Exactly. And the Mopac Improvement Project, there's another aspect to it, which is quote-unquote sound paving, where they're developing a topping slab for the road itself, which I believe is more porous, with the idea that there's less friction between the wheels and the road. So the source of sound is much smaller, and what I'm hearing in studies is that part of the improvement project is much more effective than the sound wall at reducing the amount of sound that's coming out.
And if you ever look at the tire industry, they can do a lot of things to the tire design to change the noise. Both, basically for the passenger in the car is what they care about. But you've ridden on tires that are really loud, and then some tires are really quiet.
Yeah.
So it's another interesting part of the noise. Mm-hmm. But the surface of the road also has a big difference.
So I was getting back to the power level thing. I'm kind of stuck on that. So 85 was a crazy loud restaurant. This 120 was just over the top loud theater. Like, if they wouldn't have turned it down, I would have left. I'm like, no, I'm not sitting in this for an hour and a half. And what is the threshold of pain? I mean, for me, it was around 120. Do you have a sense of that?
Well, if you look and we're covering all these aspects. So if you look in industrial manufacturing plants, industrial hygienists look at, and there are OSHA standards and requirements for the protection of the employees. At what point do you have to have a hearing protection program?
Right. Do you know that one?
I used to know, but I think 85 is where you have to have hearing protection.
And then there'll be like an 8-hour limit too. I mean,
there's a duration of time that they're exposed to it and what your average level is. And then if you get over, I don't know if it's 95 or 100, now they have to have double hearing protection. You may also have to have a annual hearing check to trend degradation. Mm-hmm. And then I think the threshold that I don't know if you can't be in, but it would be at the 115, 120 level probably.
Okay.
There's some tables you can look up to give you these levels and what it equates to a jet engine, 10 feet away versus.
So one other distinction I want to make is that you're talking about the sound power level, which is a measure of the source of sound. There's sound pressure level, which is a measure of the sound through the fluid medium, whether it's air or vibration, etc. And there's another metric in there that I'm blanking on all of a sudden. But anyway, all of those are measured, we look at them in terms of decibel. Decibel is the metric. And so one of the important things to note is that when something says it's this many decibels, we don't necessarily know, is it measuring sound power, sound pressure, or something else. And so for our purposes, in terms of general building acoustics and understanding, I think it's enough for us to read it in decibels. But for a true acoustician who's doing, say, like a high-end performance hall, or a space that's very sensitive in terms of what kind of frequencies, that simply knowing the decibel wouldn't be enough information for them.
I understand. Yeah, one's the source power, and that's the source of the sound, and then it creates a pressure in the space. It reminds me when you and I were speaking to Matthew about luminance and illuminance.
Yeah,
it's an analogous.
If you get into the analytical aspects of all this, you have to get into all those details. But the basic concepts that I like dealing with are really pretty simple. That you can apply every day, or to your house, or to anything.
Right, and that's how I wanted to wrap up. Actually, what would be some of those basic concepts for good sound design?
I think blocking sound means you add mass between you, or distance, right?
And avoid short circuits, breaches.
Avoid short circuits and paths that allow the sound to get through.
Like small gaps. So I could put double sheetrock on that wall between, this room and that.
It would make a big difference.
But if there was an outlet that lined up with another outlet, it would make
you wouldn't notice it.
Just like air sealing.
Oh, wait. So you said it would make. So if I have two outlets that line up, even though, let's say I have double sheetrock on both walls, I have 4 layers of sheetrock.
So the STC rating of that wall would be really high.
And then I could dramatically degrade it though by.
If you had back-to-back outlets that weren't sealed, you may not notice that barrier because you have an open path for the sound.
There you go. Okay. So we were.
So here's since you mentioned double sheetrock, here's a very practical piece of advice: is that frequently when people are doing design and they want to throw out a quick, easy way to increase the acoustic separation or STC value, I'll hear, "Well, let's throw another sheet of sheetrock on there." If you do that, you take a partition, you just add another sheet of sheetrock. Your STC rating goes up by about 3 decibels. The change in sound of 3 decibels is imperceptible. You would never be able to perceive that difference.
Really?
So because it's logarithmic, you need at least a 6 decibel change in STC.
Well, careful now, you're talking decibels and STC rating.
Because a STC of 55 would be a change in decibel perception of 55 decibels from one side of the partition to the other.
At what frequency?
Yeah, you're right. It gets complicated pretty quickly, but I'm thinking in terms of the human voice.
And I agree where you're going with that. Just adding a layer of sheetrock doesn't get you as much as if you put a resilient channel in a layer of sheetrock. The problem is the expense and the dimension of the wall is harder to deal with. It's cheap and easy to add a layer of sheetrock. And seal your openings is probably a bigger impact.
That's what I was getting at, yeah. So that's good. So what about the resilient channel, though? You can buy those anywhere?
Sure, those are pretty common and pretty easy to install. So that would be, as long as you have the foresight to put it in your wall section, that would be an easy method. You can also, instead of sheetrock, there's a company called Quiet Rock that I'm not sure the makeup. I think it's a higher porosity. It's pretty expensive, to be honest, but that's kind of a one-to-one switch out. Just use this instead of that, and you get a much higher.
There's a lot of
STC
things
rating
on the market, and they're composite materials usually.
Yeah.
I think there's a lot of snake oil up, or what do you call it? Like acoustical paint. Now, tell me what that is.
Yeah.
Radiant barrier paint. What about an exterior wall? What about a kind of acoustic assembly, or building assembly design from acoustic quality perspective? And I'm thinking about the acoustics of the indoor space, actually.
Same concepts apply.
So extra mass.
Extra mass, sealing the wall up, right?
Yeah,
a lot of your leaks come around perimeter.
You can cut that out for me, Miguel.
Start again. Here's an example.
Here's an example, a project I was working on in Philadelphia, where we were designing a new public high school that was right next to an elevated train line. I mean, really close to the classrooms. And so it was very important to have really good acoustic separation. And at that time, our acoustic consultant actually had us change from closed cell spray foam in the wall section to open cell because the porosity of the open cell had more absorption. So the sound transferring through that partition had a higher sound STC rating.
Interesting. And they could have shaped the outside of the building somehow to reflect sound away? Could that have been done? Bunch of convex or concave surfaces.
That would have been a tricky. Well, so that's an interesting one. Well, let me finish talking about this school, and then we'll go to that. But as we know, we talk about heat, air, moisture, diffusion, etc. with wall section. That was in Philadelphia, where you need a vapor barrier on the interior side of the section. Because we went from closed cell to open cell, we didn't have that foam being in a vapor barrier, so we had to use a plastic sheet on the interior side. You never do that around here in Austin, but
don't do that in humid climate.
Yeah, that was something we did there. Now, in terms of the exterior, when you're outside, trees and vegetation are like white noise and can mask sound. And so I'll read in books, vegetation does not work for sound blocking. It's not mass, it doesn't block sound. But I have friends who live next to Mopac, and they have lots of trees around their house. And when there's no wind, I can hear the cars rolling on Mopac. But the second it gets windy and I hear the leaves rustling, all I can do is hear the vegetation. I hear the trees, and the sound of the Mopac just disappears behind it. So it essentially acts as white noise.
I think I'd argue, though, that if those trees weren't there, it would be louder. Because those trees diffuse the sound rather than having a direct path to you of the sound.
What would be louder?
The road noise.
So the wind is creating its own
It masks the noise,
So,
but with vegetation and without vegetation, you do get some reduction.
It scatters
sound.
So I think we're saying the same thing. We're both saying that vegetation and trees are good for improved sound quality from environmental conditions.
You don't add a lot of mass, so you don't directly block the sound, but you do diffuse it, so it's not a direct line to you.
Yeah, I've seen a product on the side of buildings. It's been a few years, but it was called Quiet Brace. Have you seen that?
Oh, yeah.
It's like an asphalt impregnated or something.
Yeah, I've seen it on a couple multifamily jobs. It's, I believe, extremely cheap and can be used as sheathing, and you get some additional R value because of the makeup of it, but it's real soft, and it's I would not recommend it just because as actual sheathing it doesn't work very well in terms of your cladding attachments and applying a water resistant barrier, etc.
Diagonal bracing.
I thought you were going to go to it, and it relates back when we talked about restaurants. If you think of kitchen noise, a lot of the stainless surfaces, you hear a lot of clanging noise, which happens to be about the speech sound, and they'll dampen that by putting a mastic mass underneath on the metal so it doesn't reverberate the sound out.
Wrap up. We'll go through some final comments, and then all right. Well, I think that's about enough for wrap. Today. My final comment is actually that indoor sound quality is something that is paid attention to in the way we deliver the built world to ourselves. However, as John said repeatedly, we want more mass, and we're not putting a lot of mass generally in our walls. I mean, probably the most dense substance in most walls is the sheetrock, possibly the cladding, the fiber cement cladding. The point being that the sound of the interior is something that obviously matters. We're immersed in it all the time. And the time to pay attention to it is at design. And actually furnishings, right? You can furnish a place differently. Yeah. Okay. Well, so that was my final comment. John, anything?
I think just the idea that a lot of the takeaway maybe for most people would be the basic concepts are really simple. To understand how you block sound and how you control the reflection of the sound can make a big difference. And that sealing up openings in your wall will stop that transmission greatly also. So.
Good. Keith, final thought?
So I agree that the basic concepts are pretty simple and worth grasping. But that I would reiterate that there's two sort of common misconceptions about, number one, that room acoustics, do I want to increase the reverberation or limit the amount of reverberation versus are we talking about noise transmission and blocking sound between space? So understanding what the goal is before coming up with strategies is really important. And then the last thing I'll say is there's a great little book that is very enjoyable if anybody's interested in furthering their understanding about building acoustics by Robert Apfel, A-P-F-E-L, and it's called Deaf Architects and Blind Acousticians.
Oh, beautiful. Okay, we'll also throw a link into the show notes for that David Byrne video, that TED Talk. That was fascinating. Thank you, gentlemen. Great, wide-ranging, lively conversation. Appreciate you being here.
Thank you, guys.
Thanks.